Hi, welcome to the second part of our adventure in logistic regression model. Remember where we left off was we had covered how to do odds ratios for single simple terms, and now we're going to work with trying to understand models that have interaction terms. And this is quite challenging and quite difficult and very, very important to do it correctly. So let's talk about the example here on this overhead 32 of the current version of the notes. This is the Rate My Professor data, where the response variable again is getting a pepper rating. The student thinks that the faculty member is attractive, and we're going to explain that yes/no event variable in terms of the gender of the faculty member and the field that they study. And with the star notation here, it means that gender and field of study interact. And the summary of the model shows that we have an intercept, we have an effect for gender, we have 3 effects for discipline, and then we have interacting effects between gender and discipline. That's a total of 1, 2, 3, 4, 5, 6, 7, 8 beta coefficients in this model. If we look at the next slide at an effect plot, we see the first left-hand panel is for female faculty, and the right-hand panel is for male faculty, and it's broken into the 4 different discipline areas. And you can see that for female faculty, being in the humanities and social science has higher probabilities of them getting a pepper rating, and for science and pre-professional it's lower for female faculty. When you look at the panel for male faculty, you notice it doesn't really look quite the same. It's again higher for humanities and it's lower for science, but social science looks like it has a little bit different behavior for male faculty, and pre-professional looks like it's a little bit different. This right-hand panel for male looks different than it does for female, and that is another way of saying that the discipline effects are not the same across gender. And if that's the case, then we need to describe these things appropriately if it is complicated. So let's think about how to do that with odds ratios. Let's think about the male against female risk ratio, and let's examine it for only pre-professionals. That means that in our model, we need to specify the coefficients for male faculty pre-professional. Remember, the coefficient arrangement was intercept, male faculty, and then a discipline indicator for social science, for STEM science fields, for pre-professional, and then interactions between them. And so if we go through the coefficients for the odds model for logistic regression, we'll have an intercept term. We'll have beta 1 multiplying the gender indicator, and the gender indicator is 1 for a male faculty member. The 4th beta parameter will be multiplied by a 1 because of pre-professional. That, of course, is this parameter right here, beta 0, beta 1, beta 2, beta 3, beta 4. Beta 4 is multiplying the pre-professional value indicator, and if it's for a pre-professional faculty member, this indicator will take on a value of 1, and that's why beta 4 is multiplying a 1. And then we go on through the other betas, the interaction pieces, the multiples between indicators and gender, and for any of the disciplines other than pre-professional, those take on a value of 0. The 1 for male times a 0 for the other disciplines until we get to pre-professional, and then it will be an indicator of 1 for male times an indicator of 1 for pre-professional, and that will be the beta 7 multiplying times that 1, and that is beta naught, beta 1, beta 2, beta 3, beta 4, beta 5, beta 6, beta 7, this beta effect multiplied by 1 for male and 1 for pre-professional, that will create the right beta effect for this term. When we deal with female faculty, we will have an intercept, beta naught. The gender beta, beta 1, will be multiplying a 0 because it's a female faculty member. It is pre-professional, so beta 4 will be multiplied by a 1, and all of the rest of the terms will be zeros because we're dealing with either a female faculty member and pre-professional, and so those will all be 0. And what we're left with then in terms of betas is beta 1 plus beta 7. And that means that to fully estimate this odds ratio, we need to estimate the linear combination of these betas, substituting in their estimates, the beta hats. So this L hat is just going to be 1 times beta 1 hat plus 1 times beta 7 hat, and all of the other betas will get multiplied by zeros because they're not included in this linear combination. In order to get confidence intervals and things, we need to know the variation of this L hat, and the expression for that will be the constant multipliers list times the variance covariance matrix of the beta hat estimates multiplied by that C list again. In terms of the linear combination that we're making here, it needs to have a 1 multiplying beta 1, it needs to have a 1 multiplying beta 7, and all the other terms in the list need to be 0. And so here is the C vector that will create this comparison. This first 0 multiplies beta naught. Remember, in this odds ratio expression, we don't want the intercept. So for terms in betas that we don't want, we need to multiply them by 0. And so that's why the intercept beta naught is multiplied by 0. We do want to include the gender effect, beta 1, and so it needs to be multiplied by a 1. No other terms need to be included until we get up to beta 7, and so that's why the last one is a 1. We want to include it, and all others we don't want to include, so they all get multiplied by 0. And so C times the beta vector list will pick up the right terms, and this is how we define the linear combination of betas that we need. So we need to always make the odds ratio we want to make. This is just pure brute force making the odds ratio and figuring out which coefficients we need, and then that therefore defines the C vector. And then we need to be able to extract the estimated pieces from C times beta hat. We need to get the variance from the V-cove matrix, and then we need to make our confidence interval for L using L hat plus or minus some multiplier times the standard error of L hat. And then in order to get an odds ratio confidence interval, we need to just exponentiate this linear combination confidence interval, and we'll be then getting confidence bounds for the odds ratio. So how do you do that? Well, in terms of what we have, we create the C vector. This is just a command in R, and we specify the right zeros and ones. Then what we create is the L hat vector, which is just the C vector we just defined, times the beta hats. And the beta hats are the coefficients from our estimated model, which is RMPM3. That was defined a few overheads earlier. And so this makes the C vector times the beta hat vector, which makes the linear combination of estimates. Here is the way to program getting the variation, standard deviation of L hat. That is this expression inside the square root, and then taking the square root of it gives us the standard error of L hat. In C bounds, we are making the confidence bounds for L. We're taking the estimate of L, subtracting off the Z multiplier times the standard deviation, and then up here we make the upper boundary L hat plus the Z multiplier times the standard deviation of L hat. And we print it out. Here is our estimate of L hat. It's a positive number. And here is our standard deviation of L hat, 0.84677. Here are the lower boundary and the upper boundary. You'll notice the lower and upper boundary for L contains 0. And so that means that when we exponentiate those components, we get an estimated odds ratio of 3.25, a lower boundary for the confidence limit for the odds ratio of something below 1, and an upper boundary for the confidence limit for the odds ratio of above 1. So what does all this mean? It means that male faculty who are pre-professional, teaching in pre-professional programs, have 3.25 times the risk of being rated a pepper compared to female faculty in the same field. So higher risk of male faculty getting a pepper rating than females. The risk is above 1. So higher in the numerator than in the denominator. However, when you look at the confidence bounds, the confidence ratio, the confidence interval for the odds ratio includes 1. So it is not statistically clear that males have higher risk than female faculty in pre-professional programs. And this would be how you'd be able to describe interacting effects. You need to talk about the male against female gender effect at a fixed level of discipline. Here's another example. We have a severe storm in the Boundary Waters Canoe area. The example we're going to look at are 2 species of tree, aspen and red maple. Another predictor variable we have is the variable S, which is a measure of severity. It's the fraction of trees that are killed in a particular area. And of course, if a particular area has a very high fraction of trees that were killed and knocked over, then the storm was locally more severe in that area. We're also going to use the log diameter of the tree and that severity variable and the 2 species. And then we're going to consider a model that has an interaction between species and severity. And here's how you specify that. Y is a individual died variable. It takes on the event for died, and dying, risk of dying, is a function of the diameter of the tree, the log diameter, plus a species factor variable, which keeps track of whether it's aspen or red maple, and then an interaction effect with severity. Notice that we define a subset of the data for species equals aspen and vertical slash, or species equals red maple. So this restricts our data set to only aspens and red maples. And you can look at the coefficients here, and you can see that as the log diameter increases, there's significant evidence that the risk of death increases. You can also see that just generally for aspens, that's what the severity effect is. This is the severity effect for aspens, and you can see it's positive. As severity goes up, there's significant evidence that there's more death. And then here is the change in the severity effect when we involve red maples. And you'll notice that this is, if you move the decimal place 2 places, 1, 2, this is also a small p-value, and it suggests that the severity effect is different for red maples than it is for the other species, aspen. So there's interaction. Here is an effect plot that sort of shows you what's going on. As diameter goes up, the risk of death goes up. A little bit curved pattern, but that's what it says. Here is a panel for aspens and a panel for red maples, and plotted against severity and death risk. Here is a slightly different command that will let you focus just on the interacting effect between species and severity. And on the next page, you can see that same plot, just specified maybe in a little bit more coherent way of what effect you want to describe and how you want it described. Basically, what it shows here is that as severity of the storm goes up, there's a much higher increased aspen death risk than there is for red maple. Both kinds of trees are more at risk of being killed when the storm is more severe, but aspen behaves much more drastically and is much more affected by severity than red maple is. Red maple is affected, but not as much as aspens. Here is the effect plot for diameter isolated on its own if you wanted to see it on its own. Here's the coding for it. Well, let's think about odds ratios. Let's think about odds ratio for the diameter effect. This is not an interacting effect, but let's just take a look at what you would do. Remember, diameter is measured in log diameter, so let's think about increasing diameter by 10%. That means you're multiplying the diameter by 1.10, and the logistic regression odds function for 10% more diameter would be e to the beta naught plus beta 1 times the log of this multiple of diameter, where c is 1.10. We have a species indicator, we have a severity measure, and then we have the species by severity multiple interaction piece. The denominator is for just a diameter d, and you have your logistic regression odds function, which is basically everything the same except you don't have the log of 10% higher diameter, you just have the log of diameter. And this means that when you cancel out things like the species indicator, the severity, the species by severity, you're left with just terms involving log diameter. So remember that when you take the log of a product, it is the sum of the logs, and so you have beta 1 times log of this c multiple plus the log of diameter. Down in the denominator you have beta 1 times the log of diameter, and the beta 1 log diameters will cancel, the intercepts cancel, and you're left with beta 1 of the log of this multiple. Well, how do you get an odds ratio for that? Well, let's just first of all compute the log of that multiple so we know what number it is. And then in the expression for odds ratio, we realize that all we're going to be doing is multiplying the beta 1 coefficient by log of c, and all of the other coefficients in the model are going to get hit with 0. So intercept is not included, so it gets multiplied by this first 0. Beta naught gets multiplied by 0 to wipe it out. Beta 1 needs to get multiplied by log c. Beta 2, the species, right? Wasn't beta 2? Yeah, beta 2 is the species indicator. We don't have that involved in our odds ratio, right? Our final odds ratio does not involve species. It was a question about diameter, and species is not involved, so it gets wiped out. The severity is the next beta hat, and it gets wiped out. We don't have anything severity, and the interaction between severity and species is also wiped out. We make the linear combination of the c multiples times the coefficients for our G2 model. We make the standard error, we make the confidence interval for L, and then we make the confidence interval for the odds ratio. And you can see that the estimated odds ratio is 1.11, and the confidence boundaries are all above 1, and so it is very clear evidence that as diameter goes up by 10%, it looks like there's 1.11 times the risk of death, and that this risk of death is clearly increased because the confidence bounds for the odds ratio are clearly above 1. let's take a look at an effect that has interaction in it. Let's take a look at red maple against aspen. Now remember, red maple and aspen species effect interacts with severity, so you have to specify a severity. Let's specify a severity of 0.41. That was a pretty typical severity in the data set. That I think means 41% of the trees in the area died. Let's take a look at what the maple against aspen comparison would look like. So let's specify our odds function. It's going to have a fixed diameter, which is d, going to be both cases, numerator and denominator. Beta 2 is multiplying a species indicator, which is 1 for maple and 0 for aspen, and so that's why we have beta 2 times 1 for maple and 0 for aspen in the denominator. Severity is what multiplies beta 3, and then the interaction piece is the severity S times the indicator value for red maple, which is 1 up here in the numerator, and multiplying the indicator for red maple, which is 0 in the denominator because we're dealing with aspens. When we cancel out the terms like beta 3 and beta 1 and the intercept beta 0, we're left with a beta 2 term and a beta 4 times 0.41. Well, this is the expression for our odds ratio, and we need to calculate this linear combination, estimate, from our model, calculate the estimated linear combination, make the confidence interval, and realize that our C vector is going to have a 0 because we don't want to include the intercept. It's going to have another 0 in the second position because we don't want to include beta 1. This expression for the odds ratio does not have a beta 1, so we don't want to include it, so we wipe it out with a 0. It does have a 1 times a beta 2, so that's why we have a 1 in the beta 2 position. We wipe out beta 3. We don't have a beta 3, so we have a 0. And we do have a beta 4, which needs to get multiplied by 0.41. That's why we have that. We invoke the new coefficients. We run this code, and we see our final result is an odds ratio that is clearly less than 1. Remember, we saw that before, that at any severity, red maples were much less at risk to die than aspens. And so this is saying that red maples have 0.17 times the risk of death as an aspen for a severity of 0.41. Confidence bounds all below 1. So the interpretation here is clear evidence that red maples have less risk of death than aspens at this particular severity. Confidence bounds for the odds ratio all below 1. If you want to do this kind of computation using, it can be done using the LS means package. And here's an illustration of how you might do it. You have to load the LS means package, and you do summary of a pairs comparison of the LS means function of your model, where you want to compare the species levels. Because there's interaction in the model, you have to specify at what severity you want it, and you get output like this. And this is comparing aspen in the numerator and red maple in the denominator, which is sort of too bad because we wanted to compare maple to aspen, but LS means does it in alphabetical order, aspen to maple. And we see the flip side of the comparison, aspen 5.72 times more likely to die than red maple at this severity. This 5.72, by the way, is just 1 over the odds ratio we had previously of 0.17. If you take 1 divided by 0.17, the old odds ratio, you will get the new odds ratio. It's just a flip. And so you get essentially the same comparison. And this shows you the L hat vector in this first one, and it shows you that odds ratio again in the second one, and it shows you the individual death probabilities calculated separately in this last command. You can see that aspens are about 67% of them are going to die at this severity, and only about 26% of the red maples. Let's take a look at what we would do if we had a less severe storm, 22% of the trees dying. Then we would have the maple against aspen comparison with this coefficient vector, and we see that red maples have about 27%, 0.27 times the risk of an aspen. Again, confidence bounds all below 1. Again, showing red maples are more at risk of dying than aspen trees, but the odds ratio has changed. It was 0.17 at the more severe severity, and it's a little bit closer to aspens when the severity is not as severe. So what are we saying here? We're saying that the species effect changes depending on the severity, which is what we mean by interaction. Let's, take a look at dealing with a 10% increase in diameter. If diameter interacted with species, what would we do in that case? Well, we would have a model then where we'd have diameter, we'd have species, we'd have severity, and in this particular model I'm going to let species interact with diameter, just to show you here how you would have to expand the terms and do the math differently, because the model would be different in this case, and you'd get a different kind of odds ratio that would involve this 10% increase in diameter, but it would be a 10% increase modifying the beta 1 parameter and also the beta 4 parameter. And so if you were dealing with aspens, that odds ratio would be just involving beta 1. If you were dealing with red maples, it would be the log of C times the sum of those parameters. And so those things would have to be calculated differently, just showing you how to do that. Okay, now we're going to move on to comparing models. How can we choose one model over another? Well, we want to choose a model that's better than another one. And how do we do that? Well, it's all based on this thing called a likelihood function. And so this is an expression for the probability function of a binomial variable. In a case where we have mi trials, we have yi events out of those mi trials, and the probability of an event on this particular set of trials is theta of xi. The probability of a non-event is 1 minus theta of xi, and this is the probability function of our data. What we do to compare models is we use that probability function to sort of find out how well our model matches the data. And so what we're talking about here is a potential model in the null hypothesis that involves predictors x1 to xm, and an alternative explanation which involves those same predictors x1 to xm, but also some additional ones up to xk. And really this is a test of whether the extra predictors are helping explain the response after you've already included x1 to xm. Well, how do we tell whether those extra variables are helpful? Well, we can measure how much higher the probability function and matching function is between the data in the alternative model and the data in the null hypothesis model. And so we build this ratio called the likelihood ratio statistic, which is the variable lambda, and it's the likelihood function under the null hypothesis model and the likelihood function under the alternative. If the extra variables are really helpful, the probability likelihood function in the denominator will be much bigger than it is in the numerator. And this likelihood ratio statistic will be small if the denominator, if the alternative hypothesis model is really much better. This fraction will be smaller than 1, much smaller than 1. If there really isn't a lot of difference between these sets of predictors, this ratio will be more like 1. And we don't really use it on this scale. We typically take the log of the lambda statistic and multiply it by a -2, which, if you think about the math going on here, a value that is much less than 1 for lambda is going to turn out to be a very big positive number for -2 log lambda. So -2 log lambda values that are really big are going to indicate extra variables are helpful in the alternative hypothesis. It turns out that -2 log lambda has got a roughly chi-square distribution with k minus m degrees of freedom, where k is the number of terms. Well, it's actually k plus 1 betas in the alternative and m plus 1 betas in the null hypothesis, and so the difference in the number of beta terms is the right degrees of freedom for that test. This statistic involves -2 times the log of a likelihood function, and a -2 times the log of a likelihood function is called a deviance, and deviance has symbolism of g squared. Bigger values of deviance will indicate a poorer, less fitting model. Small values of deviance will indicate a better model. And so here is a mathematical expression for what deviance is in logistic regression in binomial likelihood functions. And let's take a look at maybe doing a test. Null hypothesis model says that the probability of an event involves the predictors in set x1. The alternative hypothesis says that those predictors x1 are involved, but there's some extra ones in this set x2. And it turns out that the test statistic is just the deviance of the null hypothesis model subtracting the deviance of the alternative hypothesis model. And if you compare that statistic to a chi-square distribution, which has the degrees of freedom, which is just the difference, you can test whether you need the extra variables. Here's a quick example from the Rate My Professor data. Null hypothesis model says that gender is not helpful in predicting the probability of a pepper rating, and the alternative hypothesis says that gender does matter. Well, when we estimate the model with gender, we can ask for the null deviance, which means take out all the predictors. And what is the deviance function? Well, it takes on the value of 276.76. When gender is included, here's the deviance. Here is the degrees of freedom when we don't have any predictors in our model. And here is the degrees of freedom when we have gender in there. And, well, here is the expression of our test. Here are the two deviances subtracted, 0.914. We need to compare 0.914 to a chi-square distribution, which has degrees of freedom 1, because the difference in the degrees of freedoms between the null hypothesis model and the alternative hypothesis model, this difference in degrees of freedom is 1 unit. So what is the probability that you would get a chi-square one-tailed distribution more than 0.914? Well, it turns out it's a pretty big probability, and that means that our data is compatible with what we might expect from the null hypothesis model, and there's just not enough evidence to say that the gender variable is needed to help explain the risk of a pepper rating. And that's how you would go through a test. Our commands for doing this would be to use a little a ANOVA command for your model, specify a likelihood ratio test, and you will see going from a model that only has an intercept to a model which has gender term in it, gives a change in deviance of 0.914. We saw that before. Change in degrees of freedom of 1, and a p-value for 0.3391. Another way to see these results is to estimate the model and just look at the model summary, and down at the bottom you'll see the null deviance, which is the null hypothesis model, which would only have an intercept in it. Here's the deviance value. Here is the deviance for the full model. Here are the degrees of freedoms. And so from those pieces you could construct a test. Notice that this p-value for the gender is roughly the likelihood ratio test p-value. What if we wanted to know if the area of study was helpful in explaining pepper rating risk beyond the gender of the faculty member? Well, we could estimate the two models, look at the deviances for the model that only has gender. Let's take a look at the deviance for the model that has both gender and discipline. We have degrees of freedom. Here is the degrees of freedom for the model that has gender, 364. Here is the degrees of freedom for the model that also has discipline. Notice the difference is 3 units, and that's because there are 3 indicator variables involved in this discipline set of effects. That's why there's 3 degrees of freedom difference. When we subtract the deviances, we get a test statistic of 6.97. When we compute the p-value, we get a 0.07 p-value, and that's difficult to interpret, but it means there is some evidence that the discipline, knowing the discipline of the faculty member, helps understand the risk of them getting a pepper rating, even if you already have adjusted for gender. If you wanted to do this test in R, it is very simple. You just use a small ANOVA command and you compare the smaller model to the bigger model, ask for a likelihood ratio test, and you get the appropriate change in deviance test statistic. You can see the degrees of freedoms, you can see the difference in the degrees of freedoms and the deviances, and you get the p-value. Another kind of command which you've seen before is the capital A ANOVA command, and remember this is being invoked on the bigger model that has gender and discipline in it. And the way the capital A ANOVA command works, let me remind you, is it takes out one set of effects at a time. So what is the test for removing gender and examining the need for gender after you've adjusted for discipline? Well, that's a 1 degree of freedom change, and it shows that the null hypothesis for this test would be to have discipline in the intercept. The alternative hypothesis would be to have the full model with gender, intercept, and discipline. And the test statistic shows no evidence that the additional gender term is helpful after you've included discipline. The discipline effect you've seen before, this same p-value and test statistic. It talks about the effect of needing discipline after you've adjusted for gender. And so the capital A ANOVA are the tests that are showing an effect after all others, a type 2 test. What we're going to work on next in the next part of the lecture is talking about whether you can tell if a logistic regression model is good or not. And we'll leave that for the next section.